Hello, this is our walkthrough in our machine learning final assignment. But before we start, we're going to go over our motivation. So, financial markets often react quickly and dramatically to breaking news. A single headline, such as an FDA approval, earnings surprise, merger, downgrade, or public offering, can trigger large intraday spikes or sharp sell offs. The goal of this project is to build a machine learning system that can predict how a stock will move within the same day based on a news headline. Using historical data that links company specific news articles, daily stock prices, trade volume, and float size, we can train a neural network to classify a percentage change in the stock.
So our target is to classify the percent differences of each stock based on the headline that comes in, or rather of the stocks based on the headlines, using a percent difference calculated by this formula. We take this and we append it onto the data frame. These values we found to be optimal for evenly separating the classifications of data. We then extract our sentiment and embedding values from Finbert. Now, without a good GPU, this can take over 24 hours on some systems. On some systems, this can take many hours. On some systems, this can take 30 minutes. So we've gone ahead, run this already, and compiled it into our afterfinfinance.csv. This is available on the GitHub repo via Google Drive link. You can download it. It is about 1 GB in size. Here we are encoding certain labels like the stock name, sector, and industry. We map it out to label encoder mappings over here. Let's go back. We append these encoded values onto our after finance onto the data frame. We also do something else, which is we combine all of our Finbert sentiments and values onto the data frame and then push it out to a new file or the same file. So this creates our merge file, and here we have it to CSV. However, since we have finance.csv here, you could name this, you could keep it the same, you could name it something else if you want to write it to a new file that is in the user's control. So this JSON is a sample output, so of course we can see there's many classes here, but we've just shown the first couple just for demonstration purposes, but all the encodings are attached onto the actual after finance or finance.csv file, depending how you set it up. The way this notebook, however, we've set it up is to help you when you want to run it. We've already compiled everything as mentioned earlier and given you the merge df as this after finance. So all the steps before this have been pre-merged into this after fin.finance CSV file, so you don't have to waste time running this yourself. We recalculate this as this is not inherently part of the CSV file. It's something that only gets appended to the data frame. Now for the scaling. So what we want here is we want to take and scale these values that are going to have a large effect on our model. So things like volume, open price, float shares, shares outstanding, market cap P ratio, daily volatility percent, and then here we have flags for certain words. Well, we have first of all our Finbert sentiments, and then we have our flags for certain words. So has FDA. This is something that would typically indicate a sharp movement. Has merger, upgrade, downgrade, has earnings, offerings, and so forth. So we combine the total scale with the optional scale, and then we're gonna split our merge data into training and validation sets. And so we'll use a 70-30 split, so 70% for training and then 30% for validation. We'll be using the standard scaler and fitting the training and validation data onto the total scale to give us these data frames. So here in our prepared data loader section, we do try to use a GPU or set the device to be CUDA if it's available. If not, we'll just use the CPU. This isn't too heavy. You can get away pretty well with just using the CPU. So here we take our embedding columns, our sentiment columns, well actually not our sentiment columns, and we'll show you why in a second, and our total scale from the previous code. Together these will make up our feature columns. The reason why we don't add our send columns here is because this is a duplicate, this is available here anyway. And then we just copy this over for our deployment features. We could add a condition here as we expand, perhaps if we maybe don't want to include certain things. And then we clear any NANs just in case. There shouldn't be any though. Then we get our xtrain and our xtrain and xval and our ytrain and yval columns. And here we're using -1 because cross entropy loss expects class indices to go from 0 to C-1 or N-1. So here we're using, for our train loader and our validation loader, we're using a batch size of 512. We found that this works quite well.
For our MLP module, we used these activation functions in a sequential manner. We used our linear to make it from this many dimensions to this to 256 dimensions. We used batch norm 1D to normalize the distribution after any shifts in the distribution after this linear. We used RALU to introduce nonlinearity for the model to learn more complex relationships. And we use dropout to disable 20% of the neurons, so the neighbors of those neurons can start to or are forced to learn without depending on those neurons, which allows us to avoid overfitting better. We then run our activation functions again for a second time for the network to learn complex abstract patterns from the features created from the first layer. We also made it so it goes from 256 to 128 to bottleneck it and to force it to produce only the most predictive information that survives from the compression. And it also helps us prevents more overfitting. That's about that can show up. And over here, we are using cross entropy loss as our loss function since we are doing an MLP. And then we are using AtomW since this is superior to the Atom optimizer. We are also using the scheduler. The scheduler lets us pass the optimizer, set the mode to min, and then set these attributes. And what this does is, over down here, you can see it uses validation loss. And how this works is, the scheduler expects the validation loss to keep decreasing, as noted by the min. And if it doesn't detect the validation loss decreasing within 3 epochs, as shown as this patience attribute, then it will try to decrease the learning rate of the optimizer by a factor of 0.5.
So here we have our training loop and our validation loop. Fairly simple and straightforward. However, we do track our the best epoch. We want to keep that, and then we store it here. And then we also want to keep the direction accuracy or track that. This is because sometimes we can get the class wrong, but we can get it right. We can say, let's say it will be very up, and it could be slightly up. So direction accuracy is also an important metric to have. Lastly, we have our mock deployment, which samples 300 random examples using our model, the validation matrix, as well as our deployment features, which were set earlier in this presentation. We get the headline, the company, the prediction, our confidence, and the actual result. So this comes in this iteration 43.7% accurate.